Hello friends, this is part 5. Today we're going to complete the paper. Okay, mathematical physics paper PHYC3A 2024 Dibrugarh University BSc 3rd SEM. Right, so we have already solved up to question number 3D. Right, today we're going to start from 3E. And before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. that's my Insta ID 123. Okay, you can follow me on Insta. So now let's start. So here is the question 3E. This is 3E. Okay, this is 3E. So evaluate, we need to evaluate this, and dA is elementary area in xy plane. Okay, so here we need to evaluate integration from 0 to 1. This is surface integral, double integration x square plus y square. So dA, so as dA is the elementary area in xy plane, so we're going to consider dA is dx into dy, right? So now integration 0 to 1, again integration 0 to 1, x square plus y square. Instead of dA we're going to write dx dy, right? Instead of this we're going to write dx dy. Then, and if we open this bracket, then we're going to write again double integration 0 to 1 x square dx dy plus, then again double integration 0 to 1, right? Let me write it properly, 0 to 1. Okay, y square dx dy. Okay, so now you see, let me write here, take this part first. Now you see, so here we have dx and dy. So this is function of x, so we can write this integral this way, integration 0 to 1 x square dx and integration 0 to 1 dy, right? Similarly, this part, what we can do, this is a function of y, so we can take this one with dy, right? Integration 0 to 1 dx and 0 to 1 y square dy, that's how we can do, right? So now integration of x square, that's going to be x cubed by 3, and the limit is 0 to 1. Then integration of dy is y, and again the limit is 0 to 1, right? Plus, then integration of dx is simply x, again integration 0 to limit is 0 to 1, lower limit is 0, upper limit is 1. Then integration of y square, that's going to be again y cubed by 3, that is 0 to 1. Okay, if we put the upper and lower limits, then what we're gonna get, 1 by 3 minus 0, right, into 1 minus 0 plus again 1 minus 0 into 1 by 3 minus 0. That's what we're gonna have, right? Let me write it properly, 1 by 3 minus 0, that's what we're gonna have. So this is nothing but 1 by 3 plus 1 by 3, that's gonna be 2 by 3. So that is our answer, right? So hope you have understood this. Now let's move on to the next question. This is question number 3F. Okay, this is question number 3F. Now find the expression for the gradient of a scalar function in a curvilinear coordinates. Hence derivative the expression for gradient in cylindrical coordinates. Okay, so first we need to find the expression for gradient of scalar function in curvilinear coordinates. Okay, so let me show you how to do this. First, let me clean these things. Okay, now you see, first let us consider 3 curvilinear coordinates. Suppose now you see we have considered, suppose we have considered u, v, w be curvilinear coordinates of a point P whose Cartesian system, whose coordinates in Cartesian system is x, y, z. Okay, and we have considered the unit vectors in curvilinear coordinate system e1 I cap e1 cap, e2 cap and e3 cap, like as we considered in Cartesian coordinate system, I cap, y cap, I cap, j cap, k cap. Similarly, we have considered e1, e2 and e3, e1 cap, e2 and e3 cap. These are unit tangent vectors to the coordinate curves at P. I will explain actually what is the meaning of this. And like I dot I is equal to 1, similarly e1 dot E is also 1, e2 dot E2 is also 1, e3 dot E3 is also 1 here. And h1, h2, h3 be the scalar factors. Let me explain why. Suppose we have a coordinate system. This is the Cartesian coordinate system. This is your x, this is your y, and this is z. Suppose we have a point P. Its coordinate is x, y, z. Suppose we have curves like this here. This is one curve. This is suppose u. This is another curve, suppose v, and this is another curve, suppose w. Okay. And these curves can be written in the form as a function of x, y, z. Right? Hope you have understood this. So now you see this plane formed by these curves like this. Okay. This is suppose you see. Let me take this as suppose. Okay. Give me a second. This is suppose u1 equal to c1. Similarly, u2 is equal to c2. Instead of u1, u2, let me take u, v and w like that. This is suppose, okay, u is equal to, right, this curve is suppose v, this is suppose w. Okay, so you see, as you see, when you say xy plane, its equation is z equal to 0, right? So if the z coordinate is 0, that means it is lying in the x y plane, right? So similarly here also you see, so if this curve is w, this is v, then this surface, that's gonna be u plus u is equal to some constant c1. Similarly, this one will be w is equal to c2 or c3, suppose. This is v is equal to c2. Okay, these curves. Now you see, as we used to have unit vectors along x-axis, y-axis and z-axis respectively, I cap, j cap, k cap. Here also we can have unit tangent vector, okay, along the curve u, that's going to be e1 cap, suppose. Along the tangent to the curve v, that's going to be e2 cap, and tangent at this point p to the curve w, that is suppose e3 cap. These are the unit tangent vectors, right? So hope this concept, you have understood this concept, such that this unit vectors, unit tangent vectors will be given by, if the position vector of this point P, which is whose coordinate is x, y, z, this position vector is, suppose this position vector, this vector is r cap, suppose r vector, not r cap. So if this r vector is, if the coordinate is x, y, z, then its position vector must be x I cap plus y j cap plus z k cap, right? Z k cap. Okay, let me use another ink. It's too faint, right? So r vector will be equal to x I cap plus y j cap plus z k cap, right? If this is the position vector of this point P, okay, that is r. Now you see, okay, so r can be written as a function of u, v and w in terms of the curved linear coordinates, in that case we're going to use the unit tangent vector. Instead of I cap, instead of j cap, instead of k cap, we're going to use e1 cap, e2 cap, e3 cap. Similarly, instead of the coordinates x, y, z, we're going to use u, v, w. Okay, so then now you see, as these are tangent to these curves, right, at this point P, so these tangents can be obtained by, you know, del u of r, which is the position vector of the point P, right? And as we need unit vector, so it must be divided by its magnitude as well. So mod of del u of r, right? And that's going to be e1 cap, right? So similarly, we can obtain e2 cap, e3 cap as del r vector, del u v of vector r divided by, you know, mod of del r, del v of r. Okay, similarly del w of r vector divided by mod of, as we are taking unit vector, del w of r. Okay, that's how we can obtain. And here you see, this can be written this way, this is into 1 by this, and this part is the, you know, scalar factor h1, right? Similarly, from here also we can obtain h2 and h3. So hope you have understood all these things. Now let me clean these things and let me write the other steps. Okay, right, let me write the remaining steps. Okay, so here you see, so these are the scalar factors such that h1 is equal to mod of del u of r, right? h2 is equal to del v of r, and h3 is equal to mod of del w of r, right? Hope you have understood this. Okay, now you see here, we can write e1 cap is equal to you know, del u of r divided by this, that means h1, right? Similarly, we can write e2 cap del v of r divided by mod of this. Okay, this is means h2, so instead of that we're going to write simply h2. Okay, and similarly e3 cap, that's going to be del w of r divided by h3, right? And you see, we know that this dr can be written as del u of r du plus del v of r dv plus, you know, del w of r dw. So hope you have understood this. As we know that suppose we have a function of x, y and z, then we can write that df is equal to del x of f dx plus del y of f dy plus del z of f dz, right? Hope you know this thing. So now this function, this r is function of u, v and w, so we can express this way, right? Hope you have understood this. Now you see, let me clean this. Okay, now what we can do here, this can be replaced by e1 into h1, right? Okay, similarly this one can be replaced by e2 into h2. Here you can see, right? If we simplify these equations, we can get this. Just give me a second. Okay, hope you have understood this. Similarly, from here we can obtain this, that is del w of dr. That is what we can do here. We can write del w of r, which is equal to, just give me a second, e cap into h3, right? So if we use these results here, then we can write del r is equal to, sorry, dr is equal to e1 cap h1 du plus e2 cap h2 dv plus e3 cap h3 dw. That's what we can write. Okay, hope you have understood this. So this is this e1, e2 and e3 are unit tangent vectors, right? Hope you have understood this. Now let me take a new slide. First let me copy this. Okay, let me copy this result dr and let me take a new slide here. So this is the last step we have got. Now you see, let us consider that phi, which is a function of x, y, z. Now here you see what we have done. We have taken this phi, which is also a function of this curvilinear coordinates u, v, w, and continuous and differentiable. Okay, and this is a scalar function, and here we have considered k1, k2 and k3 are the scalars, such that we can express grade phi is equal to k1 e1 I cap, k2 e2 I cap, sorry, e2 cap, and k3 e3 cap. Okay, now you see here, we know that d phi, if it is a scalar function, it can be written in this way, that grade phi dot dr. Okay, we can write this way. Now you see what we have got, grade phi is equal to this. Okay, so grade phi is equal to k1 e1 cap plus k2 e2 cap plus k3 e3 cap dot dr. Dr is this one. So if we write this one here, you see, so dot product of these two, that's going to be equal to, if you take this one dot this one, that's going to be equal to k1 h1, because e1 cap dot e1 cap, that's going to be equal to 1, right? Similarly, if you take this one and this one, dot product of k2 e2 cap and this e2 h2 cap dv. So here I have missed one thing, there should be a du. Similarly, second term will be k2 h2 dv, and third term going to be equal to k3 h3 dw, right? If you take the dot product of this one and this one, right? So e3 cap and e3 cap dot product of these two going to be 1, so we're going to end up getting k3 h3 dw, right? Hope you have understood this. So that's why we can write this like this. Let me write here properly. So we can write this is equal to k1 h1 du plus k2 h2 dv plus k3 h3 dw. That's what we will get, right? Hope you have understood this. Now, as I have already told you that if f is a function of x, y and z, and then we can write df is equal to, you know, del x of f dx plus del y of f dy and del z of f dz. Similarly, if phi is a function of u, v and w, we can write dv is equal, d phi is equal to, we can write d phi is equal to, let me separate this. We can write, let me write here that d phi is equal to del u of phi du plus del v of phi dv plus del w of phi dw. We can write this way. Now you see this is also d phi. So let me take, this is equation number 1, this is equation number 2, and this one is equation number 1. Suppose this is equation number 1, and from these two equations what we can do, if we compare equation number 1 and 2, this term must be equal to this one, right? What we can have, comparing 1 and 2, or from 1 and 2, from 1 and 2, what we're gonna have, we're gonna have del u of phi du is equal to k1 h1 du. Okay, and from here we're gonna have k1 is equal to 1 by h1 del u of phi, right? Similarly, we can obtain k2 is equal to h2 del v of phi, and k3 is equal to 1 by h3 del w of phi, right? Hope you have understood this. Therefore as we have taken grade phi is equal to this, so now let us replace k1, k2, k3 by these three results. Okay, therefore what we're gonna have, grade phi, that's gonna be equal to 1 by h1 del u of phi plus 1 by h2 this plus, and this term here you see, that is what we're gonna have, right? So this can be written this way, grade phi is equal to just give me a second. Okay, so we can write this is equal to, just wait, give me a second, we can write this way, this whole thing operates on phi, we can write this way, right? And from here I have missed this e1 cap, e2 cap, e2 cap, and here it's supposed to be e3 cap. Just give me a second. Okay, e3 cap. Okay, I have missed this unit tangent vectors. Just give me a second, just wait. Okay, so similarly here also we should have e1, e2 cap, and e3 cap here also, e3 cap. So gradient in curvilinear coordinates will be equal to this, which is within bracket here you can see. So this is the expression of the gradient, right? Okay, so just this is the expression of the gradient, right? Let me copy this first. Okay, so hope you have understood this. That's how we can express the gradient in curvilinear coordinates, right? And this is the gradient of a scalar function. Let me just write this one. This is the gradient of a scalar function. We need to obtain this expression only. Okay, so hope you have understood this. So now what is the next part of the question? Here you see, hence derive the expression for the gradient in cylindrical coordinate. Okay, now let us consider cylindrical coordinates. First let me clean these things, let me keep this one only. Okay, just give me a second. So let me clean all these things. First pause the video and note all these things what I have done here. Okay, now let me clean this as well. So now let me copy these two steps and let me go to the first page here, you see. So now you see, so let us consider a point in a cylindrical coordinate. This is the point P here, you can see. So rho, phi and z, these are the cylindrical coordinates. So here rho is this projection, this is the rho. Okay, this is rho let me write here row. Okay, so hope you can see it clearly. Just give me a second. This is row. Okay, and this is phi, this is phi. Okay, so row is this projection. Okay, here you can see this is this projection is row. Okay, let me write this properly. This projection is row. Okay, and so this one will be also row. In that case, this is also row, and it cuts z coordinate at z, suppose. Okay, and instead of xyz we can represent the coordinate of p in this way, in terms of rho, z, and phi, right? So we have considered this system. Okay, so we have considered the cylindrical coordinate system rho, phi, and z such that x is equal to here you see this is x, right? This is x. Okay, this must be 90 degree, and if from this triangle, that means this is x and this projection is rho, and this is nothing but y. Yeah, okay, so this is y. Okay, now you see from this triangle you can see that clearly sin phi is equal to, cos phi. Let me take cos phi. Cos phi is equal to, this base is x, by hypotenuse is rho, so x coordinate will be equal to rho cos phi. Okay, rho cos phi. Similarly, if you take sin phi, then you will get y by rho, and so y coordinate gonna be equal to rho sin phi, and z is z. This third coordinate is simply z, right? So that's what we're gonna have. So now let me clean these things. Okay, and in this coordinate system, the vector r, the position vector r, this position vector r, that can be written this way. This position vector r will be, let me separate this. Okay, so r vector will be, instead of xi cap, we can write, instead of x we're going to write rho cos phi I cap, right? Okay, plus rho sin phi j cap plus z k cap. That's what we can write. So now let me go to the new slide. Okay, let me copy these things and let me go to a new slide. Just give me a second. Let me copy this r vector. So here you see this is r vector, and let me copy this one also, this gradient of the scalar function. Let me copy this one also. So just let me copy the expression of gradient only. Okay, this one. So here is the expression of gradient in cylindrical coordinate, right? Now you see, in this case we have considered the cylindrical coordinate rho, phi, and z. So here these three are u, v, and w. For us, u, v, and w, right? We're going to consider this way. Okay, here we're going to take u is equal to rho, v is equal to phi, and w is equal to z, right? And we're going to consider the unit tangent vectors are e rho cap, e phi cap, and e z cap are the unit tangent vectors at P. Okay, we have considered. So in this case, that H1, that gonna be mod of del u of vector r. So in this case we're gonna take this one h1, instead of h1 we're gonna take this h row. So that's why it's gonna be del row of r, del row of r. So if we find if we differentiate this with respect to row, then derivative of row, that's going to be 1, derivative of row, that's going to be 1, and derivative of z with respect to row, that's going to be 0, right? If we take the partial derivative, then we're going to left with cos phi I cap plus sin phi j cap. If we differentiate this with respect to row, right, then its magnitude will be equal to root over cos square phi plus sin square phi plus 0 square. That means this only. So similarly h3, that is del v of r. So here instead of, sorry, not h3, h2, instead of h2 we're gonna take h phi. That is nothing but mod of del phi of r. Okay, so here we are taking phi as a coordinate, okay, not function that we have taken earlier. Okay, hope you have understood this. So if we differentiate with respect to phi, then what we're gonna get, rho derivative of cos, that's gonna be minus sin phi I cap, right, plus derivative of sin is cos, so rho cos phi. Now we are differentiating with respect to phi, right, z cap, and derivative of this, that's going to be 0 because it is z only, not phi. So from here what are we going to get the magnitude, how to get the magnitude, rho sin phi whole square plus, just give me a second, plus rho cos phi whole square, right? And again h3, that's going to be equal to mod of del w of r. That means in this case hz, which is nothing but del z of r vector. So here mod is, now if we differentiate this r with respect to z, what we're gonna get, let me copy this, we're gonna get k cap only. So these are not function of z, those gonna be equal to 0. So we're gonna get end up getting 1 into k cap, that means k cap only, right? So that means its magnitude is 1. Okay, 1 square, that's going to be equal to 1 only. Okay, and here you see cos square phi plus sin square phi is also 1, so that's why it's going to be also 1. Okay, and here we're going to take rho square common, then inside it we're going to have sin square phi plus cos square phi, which is again 1. So that's why it's going to be equal to rho root of rho square, that is nothing but rho, right? Hope you have understood this. Now you see, now in curvilinear coordinate expression for this gradient, this del operator, if we consider any scalar function, gradient of any scalar function, this time we will consider f, okay, instead of phi, because we have already taken phi as a coordinate. So that's why we are not going to consider as phi. Okay, here we're going to consider as f. Okay, so gradient of f, here we're going to put f. Similarly here also we're going to have f. Okay, therefore in cylindrical coordinate, gradient of a scalar function, therefore gradient of a scalar function, so let me rearrange these things so that I can have enough space to write all these things. Just give me a second. Okay, let me push upward. Okay, now let me write it properly. This is rho square, that is rho. Now you see gradient of a scalar function f in cylindrical coordinate will be given by, grade f So let me copy this one. Instead of writing again and again, let me bring this one here. Okay, now instead of h1 we're gonna write this 1. Okay, instead of h2 we're gonna put row, and instead of h3 we're gonna put 1. Okay, so that's why this will be of this form. Okay, this is gonna be the expression del row. Instead of u we're gonna have row now. Okay, here you can see I have written here. Okay, so let me write it here properly. Del row of f e1. Instead of e1 we're gonna write e row plus del here h2 is row, so that's why 1 by row into del phi of f e phi cap plus, then again 1 by 1 is simply 1, right? Because h3 is 1, h1 is also 1. So here we're gonna get del z of f e z cap. That's what we're gonna have. So this is the required expression. So hope you have understood this. So as the video is already too long, that's why I have decided to complete the paper in the next video, not in this video. Sorry for that. So stay connected and wait for the next video. Thank you.